Hello everyone, my name is Mojgan Purkeshavat and I'm going to present our recent work at CVPR titled Adversarial Backdoor Attack by Naturalistic Data Poisoning on Trajectory Prediction in Autonomous Driving. This work was done in Noah's Ark Lab in collaboration with Mohammad Sabaklu and supervised by Amir Rasuli. In autonomous driving, behavior prediction is fundamental for safe motion planning, and therefore the security and robustness of prediction model against potential attacks are important. In the broader field of machine learning, one of the main techniques for studying training robustness involving using backdoor attacks where the attacker injects stealthy backdoors into the victim model by poisoning a few samples in the training data. While the risk of such attacks is recognized as a major concern in autonomous driving and navigation, there are currently no existing backdoor attacks specifically targeting trajectory prediction models. To be effective, a backdoor attack should be unnoticeable, meaning that the backdoor injected model should behave similarly to the clean model trained on the original data. To validate this property, we measure the trajectory clean accuracy. A backdoor attack should also be effective, meaning that the poison sample should cause malicious behavior. To validate this property, we measure the trajectory attack success rate. And lastly, poison samples should not be seen as abnormal. Therefore, the poison sample should appear naturalistic and have similar properties to the samples in the original data. Our attack consists of three phases. During the poisoning phase, given a clean sample, we first generate a trigger in the form of a trajectory of a vehicle termed attacking vehicle or ATV. We refer to the samples containing ATV as poisoned samples. These samples are made stealthy by utilizing a novel backdoor disguising method to generate naturalistic trajectories with clean labels. In a training phase, the victim, unaware of the attack, trains a model on the poison dataset, resulting in a backdoor injected model. During the inference phase, given an input sample including an attacking vehicle or ATV with a malicious observation, the backdoor injected model mispredicts the future trajectory. In a detailed look into the poisoning phase, through the trigger generation step, we first select the closest vehicle to the AV as the attacking vehicle. Then, using a surrogate model, we apply an adversarial scheme to find the perturbation on the ATV's observation that yields the desired outcome. We then apply physical constraints to ensure the feasibility of the perturbations. Next, in the backdoor disguising step, we make the perturbation stealthy by transforming the road layout. Additionally, we select the clean samples with the largest gradient to generate the poison samples. We evaluate the proposed attack in the black box settings where the attacker has access to a training dataset without any knowledge of a training model. Thus, in each experiment, a different surrogate model other than the backdoor injected model is chosen. The result presented in the table reveals three main points. First, our attack is unnoticeable while being very effective. Second, the most accurate models, including PGP and HIVT, are most robust to poison training data, but most vulnerable to attacks. Third, the choice of a surrogate model does not significantly impact the attack's effectiveness. To mitigate the proposed attack, we first experimented with a detection-based defense. To do so, in a training phase, we clip and perturb the gradients of the weights that are preserved abnormal to mitigate the effect of the poison samples. As reported in Table 2, the defense impact is minimal. Additionally, we experiment with the trajectory smoothing, which is a pre-processing step serving as a defense mechanism. From the result, we can conclude 3 points. First, trajectory smoothing, even without any attack, degrades the performance to mitigate the potential backdoor attacks. Second, with disguising step, the proposed attacks remain effective and the impact of the trajectory smoothing is minimal. And third, without disguising, the attack effectiveness drops drastically, showcasing the effectiveness of the proposed disguising step. We further analyze the proposed attack through several application studies. Here, we present the experiment with different number of ATVs and different poisoning rates. From the result, increasing the number of ATV makes the attacks more effective, but also more noticeable. This is because the larger number of ATV increases the likelihood that the model learns the association between the trigger and the malicious label. Therefore, the model becomes more vulnerable to the attack. Poison rate has direct and inverse relationship with TASR and TCA. The higher the poisoning rate is, the higher TASR and the lower the TCA values are. We also analyze the effect of sample selection in the proposed attack. From the results, the proposed gradient-based sample selection is more effective, especially at the smaller poisoning rates. At the larger rates, similar samples are more likely to be selected using either random or gradient sample selection. We also conducted experiment by limiting the attacker's access to only a part of the training data. As presented in the Table 6, the ratio of effectiveness degradation is significantly lower compared to the ratio of the data access, showcasing the effectiveness of the proposed attack. In summary, in this work, we introduced the first adversarial backdoor attack targeting trajectory prediction models. We developed an extended metric to evaluate total models and conducted comprehensive evaluation on 2 autonomous driving benchmark datasets. A comprehensive ablation study was performed to assess the effectiveness of the proposed method. We also analyzed existing defense mechanisms to understand the effectiveness against the proposed attacks. Thank you for watching this video. For more details, please check our paper and feel free to ask any questions.